today's session we are going to see about the modeling of transmission line. Moving on to the modeling of a transmission line, first you have to know what are the different types of transmission line. In a different types of transmission line, you will be having short transmission line, medium transmission line, and long transmission line. In short transmission line, we will be having the voltage level that is less than 20 kilovolt and about 50 kilometers of transmission line represents the short transmission line. Medium transmission line, the voltage is between greater than 20 kilovolt to 100 kilovolt, greater than 20 kilovolt to 100 kilovolt, and the distance of that transmission line is between 50 kilometer to 150 kilometers, 50 kilometers to 150 kilometers. In a long transmission line, we will be having the voltage level greater than 100 kilovolt and the distance of that long transmission line is greater than 150 kilometers. Okay, these are the three types of transmission line. Short transmission line which has 20 kilovolt and 50 kilometers, medium transmission line between 20 kilovolt to 100 kilovolt, and the distance for the medium transmission line is 50 kilometer to 150 kilometers. For long transmission line, 100 kilovolt, greater than 100 kilovolt, and the distance is greater than 150 kilometers. See here, in a short transmission line, we will be including the value of resistance and inductance, and for medium transmission line, we will be including the value of resistance, inductance and capacitance, and for long transmission line also we will be including the value of resistance, inductance and capacitance. Why you are not going to include the value of capacitance in a short transmission line means, in a short transmission line the total capacitance will be very low and it is negligible for the short transmission line. Okay, that's why you will be neglecting the value of capacitance effect for a short transmission line, but for medium transmission line and long transmission line you will be including the value of capacitance. See here, whenever you are going to solve the short transmission line and medium transmission line, you will be taking the R, L and R, L and C, resistance, inductance and capacitance as the lumped parameter. But for long transmission line we will be taking the parameter as distributed parameters. Long transmission line will be taking the parameter as the distributed parameters. Okay. First we will discuss about the medium transmission line. In a medium transmission line, we will be having three types. First one is end condenser method, and second one is nominal T method, and third one is nominal pi method. How these three types has been derived means, the end condenser method, nominal T and nominal pi method is nothing but the placement of the capacitor is based on the if you are going to have the placement of the capacitor near to the receiving end of the system, it is called as the end condenser method. If you are going to place that lumped capacitance in the middle of your transmission line, it represents the nominal T method, and if you are going to present the capacitance, that is how you are going to divide the capacitance into two halves, and if you are going to keep it in the sending end half the value of capacitance and the remaining of the value of capacitance in the receiving end, it is called as the nominal pi method. Okay. First we will discuss about the end condenser method. In the end condenser method, if you are going to draw the electrical circuit diagram, of the end condenser method, you will be having a resistance in series with the inductance, and finally you will be having a capacitance where the capacitance is connected in parallel with the load. Okay. Now you know that the supply end voltage or sending end voltage is taken as Vs and the receiving end voltage is taken as VR. total lumped resistance is taken as R, and the reactance of the inductance is taken as XL. The current flown towards the system is taken as IS, that is a sending end current, and the current received at the receiving end, that is in the towards the load, is taken as IR, and the current towards the capacitance is taken as IC. Okay. Here also you will be taking the value of capacitance near total lumped capacitance near to the receiving end. Okay. Now you are going to draw the phasor diagram for this end condenser method. See here, first take a KVL for this loop, that is Vs vector. If you are going to draw the phasor diagram, you have to write all those values in a vector format, that is Vs vector equal to, if you are going to take a KVL for this loop, if you are going to take a KVL for this loop, you will be taking Vs vector is equal to Vr vector plus I S into R plus JXL. Okay, Vr vector plus Is into R plus JXL, and Is vector is equal to IR vector plus IC vector. See here, sending end current is Is, receiving end current is IR, and current towards the capacitor is taken as IC. Now we are going to draw the phasor diagram. In a phasor diagram, first thing we have to see about the reference vector. The reference vector what we are choosing is the VR vector. Reference vector is a VR vector. Whenever you are going to draw the phasor diagram, first point you have to choose the reference vector. Reference vector will always be at the 0 degree. Okay, that is whenever you are going to see, whenever you are going to have a protector, and if you are going to see the angle of this VR vector, the VR vector angle will be equal to 0 degree. Now you have taken the VR vector. Our ultimate aim is to draw the Vs vector. If you are going to draw the Vs vector, you are in need to draw the Is vector into R vector and Is vector into XL vector. So we have to draw Is vector. You have to draw the Is vector. Is vector, if you are going to draw the Is vector, you are in need to find the value of IR vector and IC vector. How to draw the IR vector? See here, predominantly our load will carry the inductive value of load. Therefore, whenever you are going to take a predominant inductive load, and if you are going to compare the voltage and current phasor, current will lags the value of voltage by pi r. Current IR lags the value of voltage by pi r. See here, why I am putting like this means VR is a vector where the voltage VR is appeared across this load, and IR is the current flown towards this load. The current and voltage, if you are going to compare the current and voltage, this load is, I am assuming that this load is a predominantly inductive load. So we all know that if you are going to have a resistance, current and voltage will be in phase, and for inductor, current lags the voltage by the angle of 90 degree, and for capacitance, current leads the voltage by the angle of 90 degree. Okay, since it is a predominantly inductive load, but it is not pure inductive load, predominantly inductive load, we can take the current lags the voltage by the angle of pi r. Okay, now you have drawn the IR vector. You have to draw the IC vector to find the value of Is vector. How to draw this IC vector? IC vector is nothing but, IC vector is the current flown towards this capacitor. And what is the voltage across this IC vector? VR vector is the voltage across this IC vector. Now you have drawn the VR vector, and now you need to draw the IC vector. If you are going to relate VR vector and IC vector, the current flown towards the IC vector leads the VR vector by the angle of 90 degree. Why I am telling that it is leading the current, sorry, IC leading the VR by the angle of 90 degree means it is a pure capacitor here. Here it is a predominant value of inductor, here it is a pure capacitor. Therefore, IC leads the VR by the angle of 90 degree. Therefore, you are going to have VR vector here and IR vector here. You have to draw a line IC vector. This IC vector should be perpendicular to the VR vector and it leads the IC vector leads the VR vector by the angle of 90 degree. If you are going to take this vector here, then you can able to visualize that IC vector leads the VR vector by the angle of 90 degree. Okay. Now, can able to draw the IS vector. IS vector is equal to what? IR vector plus IC vector. Therefore, the sum of IR vector and IC vector will give you the value of IS vector. IS vector. Okay. Now, you got the value of IS vector. After finding this IS vector, you can able to draw IS into R vector and IS into XL vector. IS into R vector. IS into R vector is nothing but is a voltage drop across this resistance. Okay. Now, what is the current flowing in this resistance? IS vector. IS and IS into R will be in phase. See here, for resistance, current and voltage will be in phase. Therefore, see here, I have taken this IS vector here. IS vector here. I am going to draw IS into R vector parallel to the IS vector. IS into R vector parallel to the IS vector. Okay. Now, draw the IS into XL vector. IS into XL vector is nothing but the current flown towards this inductor. The current flown towards this inductor is IS and the drop across this inductor is nothing but IS into XL vector. Therefore, voltage drop and IS. If you are going to relate the voltage drop across this inductor and the IS vector, you all know that current lags the voltage by the angle of 90 degree or voltage leads the current by the angle of 90 degree. See here, now I am going to draw the voltage drop. This voltage drop is nothing but IS into XL. This voltage is leading the IS vector by the angle of 90 degree. See here, I am having the IS vector here. I just move the IS vector here. Can able to see that IS vector and IS into XL vector, where IS into XL vector leads the IS vector by the angle of 90 degree or IS vector lags the IS into XL vector by the angle of 90 degree. Now you can able to write, you can able to draw the phasor of Vs vector. Vs vector is equal to VR vector plus IS into R vector plus IS into XL vector. Therefore, VR vector plus IS into R vector and IS into XL vector. If you are going to connect this 2 point, you can able to write this vector as the Vs vector, where Vs vector is equal to VR vector plus IS into R vector plus IS into XL vector. Okay, and you can able to write this value R and JXL will give you the value of Z. Okay, now you can able to draw the angle between Vs vector and IS vector. This angle is nothing but pi s. What is this pi r means? The angle between the receiving end voltage and the receiving end current. Pi s is nothing but it is the angle between sending end voltage and sending end current. Okay, can you able to understand? Okay. The end condenser is, I will brief it. End condenser method is nothing but you are going to connect the capacitor near to the load and you will be drawing the phasor diagram for this circuit. In this phasor diagram, you will be having Vs vector is equal to VR vector plus Is vector into R plus JXL vector. Is vector is equal to IR vector plus IC vector. First, you have to draw the VR vector and then IR vector and IC vector, then Is vector. From this Is vector, you can draw the Vs vector. That is what you have drawn here. VR vector is a reference vector and IR vector lags the VR vector by the angle of pi r, and then this IC is nothing but it is the current flown towards the capacitance. That capacitance current leads the VR by the angle of 90 degree, and Is vector is nothing but IR vector plus IC vector. If you are going to sum the two values, it will give the value of Is vector. And after finding this Is vector, this Is into R vector is in phase, and Is into XL vector is leading the Is vector by the angle of 90 degree. And finally you can able to draw Vs vector, which is equal to Vr vector plus Is into R vector and Is into XL vector. Okay. And IC vector, if you are going to find the value of IC vector, you can able to find the value of IC vector by IC equal to J omega C into VR vector. See here, IC vector equal to J omega C into VR vector. Why I am putting VR vector here means because the voltage across this capacitance is VR. That's why I am putting VR here, where IC vector equal to J omega C into VR vector. This is what about the N condenser method. Okay. The next one is nominal T method. Nominal T method. In a nominal T method, you will be placing the capacitance in the middle of your transmission line. You will be placing the value of capacitance in the middle of your transmission line. And Vs is the sending end voltage. Since you are going to separate the resistance and inductance into two halves, you will be taking the resistance value as R by 2 and inductance value as XL by 2, and here remaining value of resistance is R by 2 and the remaining value of inductance is XL by 2, and the total capacitance is placed in the middle of your transmission line. That's why you are taking the capacitance value as C, and here you will be having the load. Now we are going to write the sending end voltage, sending end current, receiving end voltage, receiving end current, and the current flowing towards the capacitor. That Vs is nothing but the sending end voltage, Is is the sending end current, and IR is the receiving end current, and IC is a current flown in the capacitor. Okay. Now, what is the value of voltage across this capacitance means you have taken the value of voltage, you are going to assume the value of voltage as V1 is the voltage across this capacitance. Okay. And the voltage across the load is taken as VR, that is a receiving end voltage. Okay. Now we are going to write the phasor diagram. So equation for the phasor diagram, that is, if you are going to take this loop, Vs vector is equal to, if you are going to take this loop and if you are going to apply the KVL for this loop, Vs vector equal to V1 vector plus Is into R by 2 plus J XL by 2. Is vector into XL by 2 vector. That is Vs vector equal to V1 vector plus Is vector into R by 2 plus J into XL by 2. And if you are going to write the KVL for this loop, for this loop you are going to write the KVL, that is V1 vector is equal to VR vector plus IR vector into R by 2 plus J XL by 2. Therefore, V1 vector, if you are going to take the KVL for this loop, you will be writing V1 vector is equal to VR vector plus the current flown towards this line is IR is a current, and IR into R by 2 will be the drop, IR into R by 2 will be, IR into XL by 2 will be the drop across this inductor. Therefore, the total value V1 will be equal to VR vector plus IR vector into R by 2 plus J into XL by 2. And current, next vector is the current vector, that is Is vector is equal to current. If you are going to take the KCL at this point, IS vector equal to IR vector plus IC vector. That is IS vector is equal to IR vector plus IC vector. Now for this equivalent circuit of nominality method, you are going to draw the phasor diagram. Whenever you are going to draw the phasor diagram, first point is you have to take the reference vector, and again I am taking the reference vector as the VR vector. Again I am taking the reference vector as the VR vector. Now I have drawn the VR vector at the 0 degree, which is a reference vector, and I am going to draw IR vector. Okay, IR vector is nothing but is the current flown towards the load. Since the load is a highly inductive in nature or predominantly inductive in nature, I can able to draw the IR vector. I can able to draw the IR vector which lags the VR vector by the angle of pi r. IR vector which lags the VR vector by the angle of pi r. And then I have to draw IC vector. Okay, IC vector. To draw this IC vector, I should know the V1 vector. Okay, I should know the V1 vector. To find the value of V1 vector is equal to VR vector plus IR into R by 2 plus J into XL by 2. See here, I have drawn the VR vector here, and the remaining thing is IR vector into R by 2 I have to draw, IR vector into XL by 2 I have to draw. IR into R by 2, IR vector and IR into R by 2 will be in phase. Same like this here. For resistance, voltage and current will be in phase. Therefore, this is the IR vector. I am going to draw the IR vector which is parallel to the IR vector into R by 2. IR vector and IR into R by 2 is the will be in phase, and IR into XL by 2. IR into XL by 2 is nothing but is a perpendicular to the IR vector. IR into XL by 2 just perpendicular to the IR vector, and V1 vector is nothing but VR vector plus IR into R by 2 plus J into XL by 2. Therefore, if you are going to write the V1 vector is equal to VR vector plus IR into R by 2 plus IR into XL by 2. Therefore, if I am going to connect this 2 point, it is nothing but is a V1 vector. Nothing but is a V1 vector. Now I have drawn the V1 vector. Now I have to draw the IS vector. To draw this IS vector, I need the IC vector. Okay, I need the IC vector to find the value of IS vector. Therefore, IC vector is nothing but is a current flown towards this capacitance. What is the value of voltage across this capacitance? It is V1. You have to know the value of V1 vector in there, and you have to draw the IC vector. To draw the IC vector, the current IC vector leads the V1 vector by the angle of 90 degree. Therefore, we know the value of V1 vector. I am going to draw the IC vector which is leading the V1 vector by the angle of 90 degree, and IS vector is nothing but IR plus IC vector. Therefore, the resultant vector, if you are going to connect this 2 points, this is a resultant vector, that is IS vector which is equal to IR vector plus IC vector. Now I got the IS vector here. After finding this IS vector, I can able to find the value of VS vector, where VS vector equal to V1 vector plus IS into R by 2 plus J into XL by 2. See, I know the value of IS vector here. Therefore, I can able to draw the IS into R by 2 vector and IS into XL by 2 vector. Therefore, first we have to draw the IS into XL by 2 vector. To draw the IS into XL by 2 vector, IS and IS into XL by 2, IS into R vector will be in phase. IS vector, this IS vector and the Is into r by 2 vector will be in phase. Is into r by 2 vector will be in phase, and Is into xl by 2, I have to draw the value of Is into xl by 2. Then Is into xl by 2 is nothing but it is a voltage drop across the inductor. There, this voltage drop will lead the Is vector by the angle of 90 degree. Therefore, I am drawing here like this, Is into xl by 2, and finally the Vs vector is nothing but V1 vector plus Is into r by 2 vector plus j into xl by 2. Therefore, Vs is nothing but V1 plus Is into r by 2 and Is into xl by 2. If I am going to connect this 2 points, this value will be equal to Vs vector, and the angle between Vs vector and Is vector is nothing but the pi s. And you can able to write the impedance of this equation also, Is vector into Z by 2, and here IR into Z by 2, IR vector into Z by 2. This is the phasor diagram for the nominal T method. Okay, this is the second methodology. And moving on to third method, that is a nominal pi method. In a nominal pi method, the third methodology is a nominal pi method. In the nominal pi method, you will be placing the capacitance near to the sending end and near to the receiving end. You will be placing the capacitance near to the sending end and near to the receiving end of the load. It is R, XL. Here you will be splitting the capacitance into two halves, C by 2 and C by 2 here. And the sending end voltage is taken as Vs. The receiving end voltage towards the load is taken as VR. And the current drawn from the sending end is taken as sending end current Is, and the current flown towards the transmission line is taken as IL, and the current flown towards this capacitance is taken as IC1, because I am taking two capacitance here. The capacitance flown here is taken as IC1, and the capacitance current flowing here is taken as IC2. And in the receiving end you will be having the receiving end current as IR. Now you are going to write the KVL for this loop. If you are going to write a KVL for this loop in a phasor form, Vs vector is equal to if you are going to write the KVL, Vs vector is equal to Vr vector plus IL vector into R plus JXL. IL vector into R plus JXL. And Is vector. Is vector is nothing but if you are going to take a KCL here, Is vector is equal to IL vector plus IC2 vector, and IL vector is nothing but if you are going to take a KCL here at this point, IL vector is equal to IR vector plus IC1 vector. Okay, Vs vector is equal to, if you are going to take a KVL for this loop, Vs vector is equal to Vr vector plus the drop across the transmission line, Vr vector plus IL into R vector plus IL into JXL vector. And if you are going to take a KCL at this point, Is vector equal to IL vector plus IC2 vector. If you are going to take a KCL at this point, IL vector is equal to IR vector plus IC1 vector. Okay. Now draw the phasor diagram for this equivalent circuit. If you are going to draw the phasor diagram for the equivalent circuit, first you have to know the reference vector. The reference vector Again I am taking the reference vector as VR vector. The reference vector should be at the 0 degree. Therefore, I am taking the reference vector as a VR vector and I have drawn the VR vector here. The VR vector, the VR vector is a receiving end voltage. That receiving end voltage is across the load and it is across the capacitance here. That is across the C by 2. Okay. After drawing the VR vector, I have to draw the IR vector. Since the load is predominantly inductive load, the IR vector lags the VR vector by the angle of pi r. IR vector lags the VR vector by the angle of pi r. Now I have drawn the IR vector. Now I need to find the value of IC1 vector. Okay, IC1 vector. To find the value of IC1 vector, I have to know the voltage across this capacitance and the current flown in this capacitance. The current flown in this capacitance is IC1 and the voltage across this capacitance is taken as VR. See here I have drawn the VR vector. Now I have to draw the IC1 vector. IC1 vector is nothing but it is a vector which leads the VR by the angle of 90 degree. Because for a capacitance, current leads the voltage by the angle of 90 degree. Therefore, for this VR vector, I am going to draw the current vector IC1 vector perpendicular to the VR vector which leads the VR vector by the angle of 90 degree. And IL vector is a resultant vector for these two vectors. IL vector is equal to IR vector and IC1 vector. Therefore, if I am going to connect this point, this value is IL vector. IL vector is the sum of IR vector plus IC1 vector. Now I have drawn the IL vector. Now I have to draw the IS vector, where IS vector is equal to IL vector plus IC2 vector. Therefore, I have to draw this IC2 vector to find the value of IS vector. How to draw this IC2 vector? IC2 vector is the current flowing in the capacitance which is near to the sending end, and the voltage across this capacitance is Vs. So if I am going to draw the Vs vector, then only I can able to find the IC2 vector. Okay. Now, what is the current flowing in this transmission line? In this transmission line, the current flowing is IL vector. Here, we have drawn the IL vector here. With this IL vector, you can able to draw the IL into R vector and IL into XL vector. IL into R vector is nothing but IL into R vector is the voltage drop across the resistance which is in phase with the IL vector. That is, this IL vector and IL into R vector will be in phase. IL vector and IL into R vector will be in phase. And IL into XL vector, I have to draw the IL into XL vector. IL into XL vector is nothing but voltage drop across the XL. This voltage drop will be leading the value of IL by the angle of 90 degree, or IL lags the IL into XL by the angle of 90 degree. Therefore, I am going to draw the IL into XL vector, where it is leading the current IL by the angle of 90 degree, or you can able to tell IL lags the IL into XL vector by the angle of 90 degree. See here, Vs vector is equal to VR vector plus IL into R vector plus IL into XL vector. We have drawn the value of VR vector, IL into R vector and IL into XL vector. If you are going to join these 2 points, that is a sum of VR vector plus IL into R vector plus J into IL into XL vector will give you the value of Vs vector. And can able to write this value as IL into Z vector. Okay. Now you have drawn the Vs vector. After finding the Vs vector, you should draw the IC2 vector. IC2 vector is the current flowing in this capacitance and the voltage across this capacitance is Vs, where the IC2 and Vs, if you are going to relate the IC2 with the Vs, Vs lags the IC2 by 90 degree, or IC2, the current leads the voltage by the angle of 90 degree. Now you have drawn the Vs vector and you are going to draw the IC2 vector. This Vs vector and IC2 vector, this IC2 vector leads the Vs vector by the angle of 90 degree, and Is vector is equal to IL vector plus IC2 vector. Therefore, if you are going to join IL vector and IC2 vector, this value will give you the total current value, that is Is vector, and the angle between Vs and Is will give you the value of pi s. And if you are going to find the value of IC1 and IC2 vector, IC1 vector will be equal to J omega C into what is the current, what is the voltage across this capacitance, VR. VR vector, IC1 vector will be equal to J omega C2, C by 2 into VR vector, and if you are going to find the value of IC2 vector, IC2 vector equal to again J omega C divided by 2, and what is the voltage across this capacitance, Vs, that is the sending end voltage, that is Vs vector. Like this you have to find the value of the capacitor current IC1 and IC2, okay. Like this you can able to find the value of the voltage, sending end voltage, sending end current, and the transmission line current, and also you can able to find the value of capacitance current IC1 and IC2 for the nominal pi method, okay. Thank you.